Space is full of dangers, and perhaps one of the most terrifying is black holes. Particularly the idea of one suddenly materializing and Earth being consumed. That's not something anyone wants to happen. After all, once this fatal cascade began, there would be very little we could do to stop the growing void, sucking in everything in its path. In time, the entirety of human existence would be completely and utterly erased from the universe, save for a handful of lonely probes and space debris left floating in the vastness of our solar system. Now, this might seem more like a movie plot than real life, but in 2008, the European Organization for Nuclear Research, known as CERN, turned on a machine they believed had a non-zero chance of creating a black hole here on Earth. The good news is that we are all still here and not hoovered up by a black hole's relentless, inescapable gravitational maw, but CERN's own webpage actually states that its machine, the Large Hadron Collider, could yet create a black hole. Have we got lucky so far? And what are the risks if we continue to push our luck in the name of science? I'm Alex McColgan and you're watching Astrum. Join me today as we explore the science of artificial black hole creation and uncover the truth about whether CERN will one day make a black hole that destroys us all. The Large Hadron Collider is an impressive piece of engineering. It's a 27-kilometer circular tunnel filled with 9,593 magnets, designed to accelerate beams of protons and heavy ions towards each other at 99.9999991% the speed of light. It can create 1 billion collisions a second and uses about 600 gigawatt hours of electricity per year, enough to power a city of over 100,000 people. But why was it built? Simple. Scientists used the LHC to recreate the extreme conditions that existed a fraction of a second after the Big Bang, but on a microscopic scale. When the particles it accelerates collide head-on, their energy can be transformed into mass via Einstein's famous mass-energy equivalence, E equals mc squared, creating heavy particles that didn't exist before the collision. These new particles survive for only the tiniest fractions of a second before decaying into lighter ones. Detectors surrounding the collision points then record the spray of particles produced in each smash. By sifting through this debris, they can work out what was created, the elementary particles that make up the standard model of particle physics. Using the Large Hadron Collider, we have been able to discover new particles like the Higgs boson, which is ultimately responsible for atoms having mass. We would never have found this particle if it were not for the Large Hadron Collider. But it isn't only about finding fundamental particles. CERN hopes to answer other questions too, like what are dark matter and dark energy? Why is there more matter than antimatter in the universe? Is there evidence of supersymmetry? To put it simply, the Large Hadron Collider is one of the best tools we have to investigate the inner workings of our universe. But whilst to many, particularly in the science community, this is a great benefit, there were some rather worrisome potential drawbacks. In particular, the risk of the LHC creating black holes. When this possibility was revealed, it instantly hit headlines across the globe. Understandably, the reaction to this was mixed. Some downplayed the risks, saying the machine, the Large Hadron Collider, was perfectly safe, or else why would scientists turn it on? Some started lawsuits, trying to legally prevent CERN from activating the LHC, although these were unsuccessful, and others made jokes about our collective impending demise. But not all this worry was entirely justified. For starters, some information that was passed around at this time was not very factual. One claim I'm going to settle for you right now is that no, CERN is not creating a portal to hell in the Large Hadron Collider, as some Facebook posts at the time claimed. You will be glad to know it was fact-checked. But while this particular claim was easily shown to be fanciful, the black hole fear is more resilient because, according to science, there is a chance it could happen. So why did CERN turn the LHC on? If there was a risk of planetary annihilation, even a small one, isn't this action in the pursuit of knowledge a little reckless? It's time to take a look at the maths and science. What actually was the risk that we were about to make a homemade apocalyptic black hole? Well, black holes are simple to make. In theory, if not in practice. In the wider universe, this happens when collapsing stars go supernova. The forces involved are ridiculously powerful, so powerful that atoms are crushed together to the point where electromagnetic forces, the force that keeps electrons away from other electrons, and even neutron degeneracy pressure, the rule that says neutrons cannot occupy the same position as other neutrons, are overcome. And with that, an important threshold is crossed. Past that level of compression, gravity is strong enough locally that the mass collapses infinitely into a singularity. And around that singularity, an event horizon forms. Nothing can escape an event horizon. Not even light can move quickly enough to outrun the curving space-time. But interestingly, while in nature we only see this happen with stars 20 times the mass of our Sun, there's no rule that we know of that says you need that much mass. Black holes can be any size, big or small. You can do it at any amount of mass, provided you can compress it together with sufficient amounts of force. In nature, we just don't tend to see those scales of forces outside of sufficiently large supernovae. But in the Large Hadron Collider, particles are smashed together with a lot of force. The question is it enough? To answer this question relies on a little maths. But don't worry if you don't feel like you're much of a maths person. Much like black holes suck in matter and light, taking in knowledge can be simple. With the help of the sponsor of today's video, Brilliant. Brilliant's online learning platform is home to thousands of lessons on maths, science, and computing. A critical mass, you might say. But rather than smash that knowledge into you like particles in a hadron collider, Brilliant's lessons rely on engaging interactive exercises that get you to try out their concepts. A method that's far more effective at getting ideas to stick than just listening to lectures. And once you have that aha moment, like mass in a black hole, those ideas will be there to stay. So if you have an inescapable appetite for learning or want to develop a productive hobby for 2026, assuming CERN doesn't end the world by then, why not give Brilliant a try? Scan my QR code or click the link brilliant.org/Astrum in the description below to learn for free on Brilliant for a full 30 days. Astrum viewers also get 20% off an annual premium subscription, which gives you unlimited daily access to everything Brilliant has to offer. Impacts in the LHC are measured using tera-electron volts, where 1 TeV is about the kinetic energy of a flying mosquito. While this may not sound like much, remember that this energy is being imparted to protons. That's a relatively large amount of energy being packed into a relatively small location. You're getting a lot of bang for your buck. When the LHC first started, particles were moving with 3.5 TeV each, for a combined impact of 7 TeV. As time went on, this was scaled up to 6.8 TeV each, for 13.6 TeV total. And this is nothing compared to what CERN has planned. When the LHC's 91-kilometer replacement, the FCC, or the Future Circular Collider, is eventually built, it's hoped it will reach a total collision energy of 100 TeV. Yes, the kinetic energy of 100 mosquitoes squashed into protons. But actually, even this is not enough force to create a black hole. Not even close. In 2010, scientists modeled exactly how much energy you'd need to smash together particles for them to form a black hole. The answer came out at 1/3 of the Planck energy, a value at which our classical rules of physics break down for atoms, and it starts becoming necessary to think about the effects of quantum gravity. As we don't yet have an understanding of how quantum gravity works, it's a bit of an enigma what happens beyond this point. Regardless, Planck energy has a value a quintillion times higher than what the LHC is able to create. So, sounds like we're safe. But if that's the case, why did CERN themselves claim that they might create a black hole with the LHC? The answer lies in the nature of reality itself. Scientists have not reached a consensus about this, but some believe that our universe is made up of the 4 dimensions you are familiar with: forwards and backwards, left and right, up and down, and time. But also a number of other tiny dimensions that are packed away in folds out of sight. String theorists are a big fan of this idea, as I've talked about in my video on the unified theory of everything. If it turns out that these other dimensions exist, a fact far from proven, though I do find it interesting to think about, it changes the maths on Planck energy and brings the value down low enough that the LHC could be hitting particles together with enough force to create black holes. So if that's true, CERN could create a black hole. And if they did, the string theorists would have some evidence to prove them right, even as the black hole started devouring the planet. So a consolation prize at least? Actually, string theorists would have a long time to enjoy it, because our planet would survive a black hole's creation surprisingly well, and there are a lot of reasons why. To begin with, there's fairly strong odds that, according to our understanding of physics, the black hole would dissipate instantly. This may sound a little contradictory. After all, didn't we say that event horizons are inescapable, and thus nothing, mass or energy, can ever get out? Initially, this was believed to be true, but in 1974, renowned physicist Stephen Hawking suggested that black holes emit a very long wavelength radiation due to quantum effects. While we've not seen this Hawking radiation directly, its wavelength is comparable to that of the event horizon of the black hole itself, which means you'd need a very big detector to see some. There is smaller scale experimental evidence using sonic black holes that says Hawking may have been right. By his theory, all black holes will eventually lose all their energy, and hence mass. Usually it takes place over extremely long timescales, but this process actually speeds up the smaller the black hole gets. By the time it's on the microscopic level, the black hole would be detonating like a tiny explosion. How tiny? Even if we imagine a worst case scenario where all the energy in a single LHC collision ended up in a microscopic black hole and was then released again, Einstein's famous equation E=mc², lets us get a feel for how much energy we're talking about. The LHC can collide 2 protons with a total energy of about 14 trillion electrovolts. This works out to be roughly the same kinetic energy of a tiny grain of sand, with a mass of about a milligram, moving at about 2 meters per second. If a black hole that size exploded in your hand, you might be able to feel it if you were paying attention. Barely. Of course, CERN is paying attention, and so would be very excited to detect such Hawking radiation in the Large Hadron Collider. They've just not seen any yet. But what if we're wrong about Hawking radiation? After all, I mentioned it's never been seen, and there is some speculation that at microscopic levels, black holes could actually stabilize instead of evaporating into nothing. Would a black hole devour the planet if it somehow stuck around? Contrary to popular portrayal, black holes are not actually all-consuming vacuums. Their event horizons are inescapable, true, but you still have to enter them in the first place. And at that scale, there is a lot more to push you out than to draw you in. Outside of the event horizon, black holes will behave in exactly the same way any other mass would. It would exert whatever gravitational pull is appropriate for its mass. And remember, we're talking about really tiny masses here, and gravity is actually a really weak force, especially compared to, say, electromagnetism. If you're not getting sucked into the cup on your desk or the phone in your hand, maybe that's a big if, you're not gonna get sucked into a black hole with the mass of a proton or two. And that's not even considering the push a black hole like that would exude. After all, black holes made of protons would still have the charge of those protons. Harvard professor Avi Loeb published an article in 2024 where he hypothesized about a black hole atom. In his scenario, a black hole that ate a proton would have the proton's charge, and thus could theoretically be bonded by an electron. Its electron would exist outside its minute event horizon, and to all intents and purposes, the black hole would exist like any other atom, although perhaps a little more compactly. Such a black hole atom wouldn't be very stable, which is a shame because how cool or terrifying would it be to have a pen made out of black holes that you could just safely hold in your hand? What it does mean is that if CERN created a tiny charged black hole, it would just fall to the floor and sit there thanks to the electromagnetic push of the floor to oppose it. That's what happens to your feet after all. But let's get rid of the black hole's charge. Along with Hawking radiation and a universe of only 4 dimensions, could we get a tiny black hole to eat the planet then? No again. I know this is almost starting to become disappointing, or at least not realistically. With the absence of charge, a black hole would not be repelled by the positive or negative electromagnetic charges given off by any protons or electrons it encountered in the floor, and this leads to a somewhat bizarre outcome. It would easily be able to fall through the floor, right to the center of the planet, and out the other side, with no harm done. To be fair, along the way, any atoms that bumped into it could be trapped within the black hole's tiny event horizon, gradually increasing the black hole's mass and thus gravitational pull. So this theoretically could result in a growing black hole, but realistically, it's very unlikely to happen because, it turns out, even in the absence of charge, the odds of the black hole hitting another particle in the first place is minuscule. Consider the fact that 100 trillion neutrinos pass through your body every second, and yet over the course of your entire lifetime, the odds of a single neutrino actually bumping into one of the atoms that make up your body is about 1 in 4. That's ridiculously tiny. This is because atoms are actually mostly made up of empty space. Think of an atom's nucleus like a marble sitting in the middle of an entire sports stadium, and so normally only interact thanks to their charge. Neutrinos have no charge, just like our neutral black hole, and so just pass through that space. Marbles in sports stadiums are hard to hit. It is theoretically possible that our black hole would get lucky and encounter the occasional atom over the course of its quick journey through our planet's core. But even if it stays, it is unlikely to gain any appreciable mass before the planet dies when the sun turns into a red giant in 5 billion years. And there's one final crushing blow to the idea that CERN is going to create a black hole that will destroy the world. CERN could form a black hole by hitting particles together, but we as a planet are bombarded by fast-moving particles all the time. Particles thrown our way from space will hit particles in the atmosphere at a comparable level to what the LHC is doing. If that process could actually create a black hole, it would probably have already done so by now. So, there you have it. If reality has more than 4 dimensions, and if Hawking radiation doesn't exist, and if CERN created a black hole with no charge, and if that black hole fell and got really lucky, then yes, CERN could create a black hole that would consume the world from the inside out, coring our core and undermining our crust until everything and everyone dropped into a void beneath our feet. but it probably won't ever happen. In truth, there have been times when scientists have taken risks that their experiments could cause real harm, even as they pursued scientific understanding. This is why we try to avoid recklessly running experiments on humans, particularly if there are no guardrails in place. But hopefully you now agree that CERN and the LHC is not one of those times. The odds of them creating a black hole are just too low, and even if they did, there would be practically no danger. So I think we can safely say that we are not at any risk from CERN, unless they finally open up that portal to hell. Maybe to be on the safe side, we should look into that theory instead. Thanks for watching. We mention this a lot, but that's only because it genuinely makes a difference. Astrum runs because of people like you who take a moment to join us in what we do. So consider taking 1 minute to look at the Astrum Patreon and see if any of the tiers and rewards interest you. Every member is core to our videos, and you get to watch all of these videos completely ad-free. We truly couldn't make these videos without you. If you enjoy what we do, come join the Astrum community today.